without drift and train. What is the model with drift and train? What is the drift? Drift represents intercept. So you can write a model with drift. So you have an autoregressive process. You are trying to write. This is called a drift, okay, or an intercept plus, say for example, delta I train. So this is train plus rho yt minus 1 plus epsilon. So this is a very general model. A model which has a drift, which has a train, and plus the dependence of yt on yt minus 1. And that's why we call it AR1. Auto means self. Regressive. Do you understand what autoregressive means? The term auto means self. Means regression on self. So auto, regression. So yt minus 1, because I have minus 1 here, I write it order 1. If I have yt minus 1, then yt minus 2, I write it autoregressive of order 2. So let me start with a very simple model where I have no drift and no train. So this is what is your model now. That means so this model yt equal to rho yt minus 1, it has no intercept, no train. Now let's assume that your rho that connects yt and yt minus 1 or the coefficient that explains the dependence between yt and yt minus 1. Let's say this is equal to 1. Exactly the same thing that I explained before, like unit root behavior. So in this case, yt has a unit root. If you can describe yt equal to yt minus 1 plus epsilon. So rho equal to 1, so then rho equal to 1 here, yt minus 1 epsilon. Now let's try to think about two time periods. So at t equal to 1, so here t equal to 1, t equal to 1. So 1 minus 1 equal to 0 and t is 1. So at time period 2, what happens? So we write yt. So yt equal to 2. So 2 here. Then rho yt minus 1. So 2 minus 1 is 1. Then epsilon 2. Now you can replace the value of y1 equal to y0 plus epsilon 1 here. So you have y2 is equal to y1 plus epsilon 2. So in this case, just replace this value. So you can have y0 plus epsilon 1 plus epsilon 2. Likewise, if you have t equal to 3, 4, 5, 6, 7, 8, likewise. So you can just write y0 plus epsilon 1 plus epsilon 2, 3, 4, 5, 6 until t, which can be large. Is it clear now? Yes? So repeated substitution of the values of yt in a unit root case. So what you have here, yt, you can write as y0 plus infinite or a very large substitution of the values of epsilon I. So yt equal to, in this case, when rho equal to 1, so y0 plus sum of epsilon I equal to 1 to 2. So where t can be, say for 1, 2 here, so you can have 3, 4, 5, 6, 50, 60, 100, any number. Okay. So ultimately, what we are trying to do is that you are expressing the value of yt in terms of infinite values of the error term. So in effect, so you have t equal to, say for example, infinity, a very large number, so 2, 3, 4, any number here. So you have initial value y0 plus sum of t equal to, say, here you have, say, 1, 2, so you have infinity, then epsilon. Okay, so it is, in this case, so e1 plus e2 plus e3, likewise, plus e infinity, infinite. So if a time series began 50 years, 60 years, 80 years ago, so you can have something that happened 8 years ago, it's still happens. Okay. Now there is a mechanism to prove here. can you tell me what is the variance of epsilon? What is the error? Epsilon is the error term. So the variance of epsilon is sigma square. You have learned that in your class calculation, right? So variance of is sigma square. Now what I will try to do, that any observed time series yt, it can be explained in the presence of a unit root. So you now learn that yt equal to rho yt minus 1. When there is a unit root process, yt has two components. When rho equal to 1 or a unit root. So in this case, we have two components. Yt is explained by y0, means initial value, and then yt also is explained by the sum of the error. So in this case, we just write y0 plus sum of this error. These two components explain the variation of y. Now, there is an important thing to discuss. Remember, whenever a series is non-stationary or unstable or unit, then the fluctuation of the behavior of the series is completely or sensitively determined by the initial level. Depending upon what is the magnitude of the initial level, the behavior of the time series behaves. Okay, so very irritating. This theory in economics, which is called a kind of big push theory, or initial in mathematics, initial value theory. Some of you, if you have followed some higher mathematics, so you might have heard about initial value theorem. And in statistics, here in economics, we call a big push theory. What it says, if we are discussing about the investment of an economy today, so we should think about what was the initial investment and some other factors. Depending on what was your initial investment, the magnitude of the current investment will depend upon initial investment. The magnitude of current income depends upon your initial income. Your current knowledge depends upon your fundamental knowledge. So if you want to be really intelligent today, I'm expecting you must have your basics right, fundamentals right. That's why I posted this one in the blackboard. So I'm trying to describe a unit root process, isn't it? So yt is very much sensitive to initial condition. This is what we call initial condition. In physics, this condition is called a butterfly effect. Have you heard this name? Yes? The sensitivity of initial condition on the current value of a time series. In physics, this is called butterfly effect. Butterfly effect is an effect in physics where with the tiniest flap of the wing of a butterfly, the course of a storm changes. Okay? If there is a storm, the scientists say the path of the storm, the trajectory of the storm can change depending upon a small or tiny flap of a butterfly. It can be so sensitive. So butterfly effect in terms of measures the sensitivity of initial condition on the current trajectory of any time series. Okay, that is what we call butterfly. In our case, if a series is governed by unit root process, so initial condition, specification of initial condition is a very important thing. Depending upon this, you can show whether the series is just like that or stable. So initial, why we start from initial condition, y0, that is very important. Now, I will try to derive under this condition two things. What is the mean of the process? What is the variance of the process? Because I told you that a unit root can be detected by looking at the mean and variance. I told you before that, so unit root you can know by two things, non-constant mean and non-constant variance. Yes, that's what I told you in the beginning. So in this case, if my model is given by this process, then I will try to explain that from equation 4, the mean is something, variance is something. How do I derive that? That can be one of the questions in your lecture. And the derivation is extremely simple. So basically, we have described with repeated substitutions. Yt is given by the initial value y0 and then the sum of say t equal to 1 to say t, then you have epsilon. Okay? So what I do now, I try to take an expectation. I want to find the mean. So first thing is find the mean. That means expectation of y0. So then I write expectation of y0. Expectation here, expectation here, expectation here. Plus expectation of sum of epsilon. So e equal to 1 to 30. Okay. The average or the mean of a constant is what?
Itself.
It's a simple statistical stuff. So if I want to take the mean of a constant, it will be constant itself, isn't it? So in this case, y0 is a value, constant value. So then I can have here y0. Then I have expectation of sum of the error terms. So let me expand this one. So this will be expectation of E1 plus expectation of E2 plus expectation of E3 plus expectation of likewise say expectation of epsilon. Okay. So this is a sum. So E1 plus E2 plus E3, 4, 5, 6, 7, 8, 9, like that. So expectation of 1, expectation of 2, 3, like that. By classical assumption from classical linear regression, you know that expectation of the error term is 0. Yes? So from OLS, ordinary least square regression, one of the basic assumptions is that expectation of the error term is always 0. Isn't it? How did you know? Because I also told you that error term is normally, independently, identically distributed with mean 0 and variance sigma square. You have known that one from ordinary least square estimation. Right? From classical linear regression, we knew error term is IID, so it has mean 0. Okay?
The sum of the error terms to be 0, you have to allow the model to have an alpha.
Sorry?
To have an alpha.
Arjun?
An alpha, or that should be 0.
Oh yes. Yes, we can. So now listen. So the fact is that when expectation of epsilon is 0, it means that positive error and negative error of that time they just vanish. Okay. So this one is 0 plus 0 plus 0 plus all of them 0. So finally, what we get, expectation of yt is only equal to yt. This is what you have here. Expectation of yt equal to yt. Now we need to find the variance. Variance of yt. So variance of yt, once again, it's very simple. So variance of y. So how do I write variance? Variance equal to expectation of yt minus expectation of yt, this one, square. So this is basically the mean. So what we will do, expectation yt minus the mean, then square it, and then take expectation, that will be your variance. So what I will do here, what is your yt here? We know yt equal to y0, yes, plus sum of epsilon t equal to 1 to t. So this is yt, we know that. Yes. From this expression y0, you can write like I equal to I or t, whatever you like. Okay? Doesn't matter. So now t equal to 1 to t. Now what I will do, this is yt. So it's minus expectation of yt. Expectation of yt is y0. Yt. Bracket close. Take expectation here, square. So y0 cancels. Okay? So this is your, from this expression. Expectation of yt we derive, which is y0. So y0 cancels. So only thing we have here, expectation of sum of epsilon t square, which is equal to, tell me. So sigma square plus sigma square 1 plus sigma square 2 plus sigma square 3. Likewise, continue doing like that. And so if I add all of that, it will be t sigma square. So if I have t number of time series, 50 years, 60 years, so it will be t sigma square. Is it clear? Yes? Is it okay? You understand? So it's very simple. So I have et, so t equal to, if I have t equal to 1, I have sigma square 1. T equal to 2, so you have sigma square 2. T equal to 3, sigma square 3. T sigma square 3. So then t, it will be 1, 2, 3, 4, 5, 6, 7, all of them. So t sigma square. How many that? So there is a beautiful property here. The thing is, you can see from here that whenever we have a time series given as yt equal to rho yt minus 1 plus epsilon t and rho equal to 1, then its mean is initial value, variance is t sigma square. So let's say when t is infinity, t sigma square tends to infinity as well. So for a non-stationary time series, so the variance is always, it can always tend to infinity. When time becomes large, over time the variance becomes extremely volatile, extremely large. Today if it is, the variance is, the fluctuation is 2%, tomorrow 3%, day after tomorrow 10%, then after 20 years of time, 50 years of time, there is fluctuations or uncertainty everywhere. That is what we call. Okay. So this is one thing. We can get exactly the similar type of situation whenever we introduce a drift. So we concentrated on only one, no drift, no trend. Now if we change our situation.
I have a question.
Yes.
In this calculation, what happens to the other binomial terms? If you have something like this, a plus b squared, and there's this term. So it's not only a squared plus b squared, but there are other terms in this term, aren't there?
Why do you want to?
Like if you wrote like the sum of something squared.
Yes.
So if you sum it first and square it afterwards, then you have more terms.
Your friend has told me very, very important thing. Yes. Let me divide it. So let's say U1 plus E2 plus E3. Right. Okay. Okay. So E1 square, E2 square, E3 square, then 2, say 3, this one, this one, this one. Cross section of. So let's say only we have two terms here, E1 plus E2. So you have E1 square plus E2 square plus 2 E1. Take expectation here, expectation here, expectation here. So then this is sigma square 1 plus sigma square 2. Then expectation of covariance of this one is 0. By assumption from OLS that the covariance between two error terms is already 0. That is because, this is because the expectation of E1 and then expectation of E2, this is 0, this is 0. Okay? So then I am assuming E1 is independent of E2. If that is so, then expectation of E1 times expectation of E2 is similar here, expectation of E1 times E2. So this is because that's why we disregarded that. I assume that you know that the covariance of the residual, the expectation is 0. I assume that you know that. Does it make sense? Yeah. Okay. Because these are simple ways, simple classical linear regression that you have learned. That basic assumption from OLS is this. I thought you have remembered those things. So, OLS assumptions about error term. So error term is expectation of E equal to 0, and then expectation of EI and EJ. One error term, another error term. T plus 1, T minus 1, whatever. They are also equal to T. Based on the fact that EI is independent of EJ. That's why I said IID, independent error term. If that is so, and then their covariance. So covariance of EI and EJ, or in this case T and T minus 1. So E1 or E2, whatever you say, that should be equal to J. That is what we derived. Okay. You should show, if this type of question comes in your exam, show all these calculations. But I must thank your friend. What's your name? I must thank you because there are some situations where the covariance is not equal to the covariance of the error terms. And that is where this independence assumption does not hold. So if E1 is not independent of E2, is not independent of E3, in this case, we have a very complicated variance covariance system. In fact, that in this case, whenever E1 is not independent of E2, is not independent of E3, likewise, then you have something called variance, covariance matrix. And the matrix is represented like that. Sigma square 1, then sigma square is 1, 1, sigma square 1, 2, sigma square 1, 3. Likewise, sigma square 1, n. Then in the principal diagram, again here you have sigma square 2, 1, sigma square 2, 2, sigma square 2, 3. Likewise, sigma square 2, n. Then continue like that, sigma square n1, sigma square n2, sigma square n3. Likewise, sigma square nn. So this is what called covariance between E1 and E2. Covariance between E1 and E2. And if they are not equal to 0, when E1 and E2 are not independent. But in a restrictive situation where I derived this one. In this case, I assume that all of them are 0. So I accept the fact that sigma square 2, 2, sigma square 3, 3, sigma square n, all other elements are 0. Okay. That is the idea. So the covariance of epsilon 1, 2, 2, 3, 3, 4, 5, 6, anyway, all these terms are 0 with the assumption that E1 is independent of E2, likewise independent of E1. If they are not independent, then you will have all these terms. If they are not independent. But want a simply very simple case. So, very good. I appreciate that. If we do not have a thinking student, how can I be challenged? That's a very good thing. Now let's go to the second case. So in this case, the only difference is that I am just adding only an intercept. So this is a case of a time series when I have an intercept or drift, but no time. And so similarly, you can have rho equal to 1. When rho equal to 1, you can write yt equal to alpha plus yt minus 1 plus epsilon. So I'm just putting rho equal to 1 here. Once again, say t equal to 1. So in this case, just follow the logic. Yt, so I write y1 equal to alpha plus 1 minus 1. So I0 plus epsilon 1. Say t equal to 2. So I have y2 equal to alpha plus y2 minus 1. So 1 plus t equal to 2. So epsilon 2. Okay? And so what I can do here, this one, y1 equal to this much, I replace it here. So I can express y2 equal to alpha plus, then tell me, alpha, then plus y0 plus epsilon 1. So y0 plus epsilon 1 plus then I have epsilon 2. Likewise, keep on substituting t equal to 3, 4, 5, 6, 7, 8, any n number of things. And then at the end, once again, you will end up expressing yt in the form of the sum of the error term. So you will have y0 plus t alpha, means 1 alpha, 2 alpha, 3 alpha, like that. See, where I express y2 equal to alpha plus y1 plus epsilon 2. So which is equal to, replace y1 equal to that right hand side here. So it will be alpha plus alpha, y0, epsilon 1, epsilon 2. Alpha plus alpha is 2 alpha. So if you are substituting for t equal to 3, so 3 alpha, 4 alpha, 5, 6, 7, 8, t alpha. Okay? And then this side. So then once again, let's try to derive in similar way. So expectation of yt. So this will be equal to expectation of y0 plus expectation of t alpha plus expectation of the error. Okay, sum expectation of the sum of the error. Okay, so we know expectation of a constant is y0, t is a time, a number, alpha is a intercept number. So this is a constant. Again, t alpha, and this part is 0. Once again, by the assumption of classical linear regression, expectation of the error term equal to 0. So this part is 0. So the mean of the process is now y0 plus t. So whenever I introduce a drift term, so you can have y0 plus t alpha. Earlier, when there was no drift term, so you can see expectation of yt was only y0 before. Okay? Just see this one. So in this case, we did not have any intercept. So expectation of yt equal to y0. Now we introduce y0 plus t. But the variance will not change anything. So see the calculation once again. So the variance again. So expectation of yt minus expectation of yt square. So that is what your variance is. So your yt in this case, given this expression, equation 6. So this is y0 plus t alpha plus sum of et. Okay. So this is your this part. Then minus expectation of yt. Expectation of yt we have found is y0, then plus t alpha, so the minus and plus, that becomes minus t alpha. So square. That one cancels, that one cancels. So finally, we have expectation of Et square, which is equal to T sigma square. Just following exactly the same logic that we did before. Okay? So whenever we introduced an intercept in a unit root model, only the mean of the process changes, but the variance remains the same. Variance remains the same in the sense that as t increases, variance also rises infinitely. And finally, if you have a model with intercept and with a trend, both trend and intercept, you will see that the variance as usual remains constant, but the mean of the process changes. And in this case, the calculation is little interesting here. Let's derive how. Can I tell you something? Can I ask you, how do you add from, say, 0 to 10? If I want to add them, can you tell me that 0 plus 1 plus 2 plus 3 plus like that? So what will be the number? How do you do normally? Add all the numbers.
N divided by 2.
So n times n plus 1, 5. Isn't it? Yes. So if I just want to add all the things, so 1 to 10, 1 plus 2 plus 3 plus 4 until 10. So then n is equal to, so n times n plus 1 by 2, which is equal to 55. Okay, 10 plus 1, so 110 by 2 is 55. We have used exactly the same type of stuff here, same type of calculation. Let me show you how. So what we do here once again, so our model is YT, we have both intercept and trend. By the way, what does trend mean? What is trend in a time series? We have learned it. Trend represents a kind of long-term movement of a time series. Long-term movement. And so, in this case, let me say that I am assuming rho equal to 1. So, if rho equal to 1, so 1 times this is exactly the value 5 is going to happen. So, once again t equal to 1, so y1 equal to alpha plus beta t plus y0 plus epsilon 1. Similarly, t equal to 2, so y2 equal to alpha plus beta t plus y1 plus e2. Correct? So that's it. Write 2 here, and then can I write, am I correct or not? Or shall I just write t here or replace 1 here? That's right. And here?
And 2.
Very good. And so, and 2 minus 1. So again, substitute the same way that y1 appears here. So substitute all these values here. So you can write y2 equal to alpha plus 2 beta, then plus again alpha plus beta plus y0 plus epsilon 1, then I have epsilon 1. So then I have alpha 2 beta, beta 3 beta, then y0, that's 2e2. Okay. Continue, so like that y3, whatever value y2 here, so then you can express it. So how do I write y3? So y3 I can write like that, alpha plus beta, 3 beta plus y, t minus 1 means 2 plus epsilon 3. So whatever you get from y2 here, all these things replace here. Likewise, keep on substituting, repeat once again. And finally, you will get an expression which is equation 8. So if you add all of them together, so you have T alpha. So if you have T equal to 1, 2, 3, so 3 alpha. And the rest, you have say 2 beta, 3 beta, 4 beta, keep on adding them. So it will be T times T plus 1 by 2 beta, and this part will. So this is how you will add up the continuous numbers. So n times n plus 1 by 2. In this case, we have T times T plus 1 by 2. So once again, take expectation of y. So the mean will be expectation of T alpha plus expectation of T times T plus 1 by 2 beta. So this is the expectation, and then I will have expectation of 0 plus expectation of sum of epsilon. So once again, this is the same plus, this is a constant, the same thing here, constant, same thing here, and this one is by assumption of the classical regression. This is 0, so these are all constants, so we should have everything here. That's why expectation of y equal to y0 plus t alpha, all these things. And then the variance, so what will you do? The variance is expectation of yt minus expectation of yt, the whole square. So exactly the same procedure that we follow. So expectation of yt minus expectation of yt, that this is your mean, the square. So this is variance of yt. So our yt, given our expression equal to t alpha plus t times t plus 1 by 2 beta plus y0 plus sum of epsilon. This is your yt. Okay? So take away expectation of yt. Expectation of yt is all these elements. So we have minus t alpha minus this component t times t plus 1 by 2 beta minus y. Then, so this is your expectation of y. So take square. So this cancels. What is remaining here again? So expectation of it is square, which is this much. So to sum up, what we got? We discussed about 3 different variants of autoregressive processes. 3 cases. Okay. So the first case, no intercept, no train. Maybe I can write down clearly here so that you understand. One of them will be in the exam, so please prepare them well. Okay. So this is our very restricted process, and I am assuming rho equal to 1. So we discussed 3 cases. First, no drift, no train. So in this case, we derive expectation of yt was, tell me, y0, and expectation of, variance of yt was 1 to t sigma square. Now, we discussed case 2. We have drift, but we had no train. So in this case, we found expectation of yt was equal to, what was that? Mu0 plus t beta. Is it something is that? T alpha. So we had mu 0 plus T alpha. That's the mean and the variance of yt, what equal to T sigma square. And finally, we had a very general model. So in the last model, we had both drift plus trend. So in this case, expectation of yt was all the things that we had discussed about. The final case, that is the one. That means equal to, we had y0 plus T alpha plus T times T plus 1 by 2 beta. Okay, so this is your mean and the variance, of course, T sigma square. So you can see in each case, drift plus trend T sigma square, drift no trend variance T sigma square, no drift no trend variance T sigma square. That does not change. Only change we have from y0 with no trend, no drift. Then yes, it will be y0. Okay, y0. So y0 plus T sigma, that is for drift, no trend. Then y0 plus T sigma, there is some function of the trend here, and that is with drift and so this is the only. A question may come in the exam, something like this. So the question will be of this form. Remember that in the blackboard, I have some worked out examples from previous year question. So there is a previous year question. I have solved that question. The answers are always there. Okay. So the question may be something like this. Assume that you have a time series which is yt equal to alpha plus beta t plus say rho yt minus 1 plus epsilon. So this is a kind of question which may appear in the exam. And the question can be something like this. Assume that rho equal to 1. So derive expectation of yt and variance of yt when alpha equal to 0. Derive expectation of yt when say beta equal to 0. So in the first case, you are trying to assume derive a mean and variance when alpha equal to 0. So in this case, you will have only the trend term. In this case, you are just having only alpha, no trend. So then alpha, no trend, and rho equal to 1, assuming this one, then you have to write the model. Let's talk about this model now. Derive expectation of yt when beta equal to 0. So when beta equal to 0, how do I write the model? So yt should be equal to alpha plus yt minus 1 plus epsilon. I am assuming already rho equal to 1. So your model is yt equal to alpha plus yt minus 1 plus epsilon. So then just try to find expectation of yt in this case. So in this one is exactly the same thing as a model. So it is exactly the same type of model. So model with drift but no drift. So these three cases you learned today. An autoregressive model when there is a unit root, rho equal to 1, we derive mean and variances of this process in three situations. The first situation was no trend, no drift. Second situation was trend, no drift, but trend. First situation, all of them. And we found only the mean of the process differs, variances remain the same across the derivations. So that should describe That should be fine for your today's lecture. Try to remember all those things. Then this Friday, I will try to find the estimation and testing procedure for unit. We'll do some test. I will get my computer. We'll do some using some real life data. I will show you how to test. But remember those equations, extremely important for your exam.